Welcome back to Separations class. This video is a review of how to perform an energy balance. This is a critical step for engineers to perform an economic analysis on their processes because energy is the main operating cost of a separation process. So the term operating cost is one that we'll come back to again and again this semester, but it's one of the two main types of costs in designing a process. The operating costs are all the recurring costs that you have to pay for as the process is running. So because energy has to be input or taken away, that is the main driver of what this cost is. And as you'll learn in your economics class, you have to know how much it costs your process to run because you want to make sure that you're selling your product at a price that is going to turn a profit. So let's start with our process flow diagram of our flash distillation unit. I'll call it a single stage distillation unit. So we have our feed coming into the process at some temperature T0 and some pressure P0. Inside the distillation unit, I am running it at a certain process temperature and pressure. And because the outlet streams are assumed to take the process conditions of the process unit, my vapor and liquid outlet streams are also at some T and P. Now, because typically the feed is liquid, and I discussed reasons for that in a previous video, a liquid is just easier to handle in general, so most oftentimes you'll see the feed be a liquid. It doesn't have to be a liquid, it could be a vapor, but I'm just saying that liquids are more common. You'll have to therefore increase the temperature in order to get phase equilibrium to occur. And if temperature is increasing, that means you probably have some sort of heating element or heating coil that is inputting energy to the process. But you could also have cooling water or something that is taking energy away. So the main components of an energy balance start with any other type of balance, and that is with the general balance equation. So that was in plus gen minus out minus consumption is equal to accumulation. Again, hopefully bringing up good memories from MEB class. And because we're talking about energy here, remember, I cannot generate nor consume energy, so those terms are going to cancel right away. My input and my output terms I can say is my net input of energy. So my terms here are my heat term, so that's the amount of energy that I'm putting in or taking out. And then I also have to add shaft work because that is another way that you could input energy into the system. However, for most separation processes, this is able to be canceled. So no shaft work in phase-based separations. But if you had shaft work, it would go there. We won't see that too much this semester, so no shaft work. All right, so that is my net input or output of energy. The accumulation energy I can think of as my sum of the changes of kinetic potential and internal energy. So I can say equals the sum of delta EK. I'm not going to write it as a sum. Delta EK plus delta EP plus delta H dot, where EK is kinetic energy, EP is potential energy, and H dot is enthalpy. And as chemical engineers often do, we are going to assume that the kinetic and potential energy changes are going to be negligible compared to the enthalpy changes. So even though there may be small differences in kinetic or potential energy in the single stage distillation unit, those are going to be much smaller than the enthalpy changes that we have. So just like many problems in material balances, we end up with the familiar equation Q is equal to delta H. And I can expand this delta H by writing it as the number of moles times delta H under bar. So H under bar, remember from your thermo class, is molar enthalpy. So this will be in units of kilojoules per mole, for example. All right, and now we are ready to start evaluating this. So in order to calculate the energy requirements of your system, you just have to calculate what the change in enthalpy is. Now, this is going to be a slightly more difficult process, and it's going to be something you have to keep track of. So the best way to do that is by drawing yourself an enthalpy table, just like we did in MEB. So let's go ahead and make a table of inputs and outputs. So in, out, let's do moles and enthalpies, molar enthalpies, H underbars, moles out and H underbars out. And we need our components. So we've got component A and B, obviously. However, we have to account for the fact that we are vaporizing some of it. So we've got vapor component A and vapor component B, and also liquid component A, liquid component B. Okay, so let's start filling in this table. In the inside, we only have liquid, I'm going to assume. So assume feed is liquid. And obviously this would change if the feed was vapor. Assume liquid feed. So we have 0 moles of vapor coming in. So I can put 0 on the table. For liquid component A, the number of moles in terms of the process variables that we typically have is ZA times F, the molar flow rate. Similarly, the moles of liquid component B that we've got coming in is going to be 1 minus ZA times the molar flow rate F. We're assuming it's a binary mixture, so only 2 components. Now for the enthalpies, if I don't have a molar flow rate, I don't need to figure the enthalpy. I'm just going to call these H1, H2 for now, right? And then figuring out what H1 and H2 are is going to be another challenge that we'll get to in a moment. On the outside, I have vapor component A coming out. YA times V is the molar flow rate of vapor A. 1 minus YA times V is the molar flow rate of vapor component B. See if you can figure out what the liquid components are going to be. You can probably guess it's XA times L and 1 minus XA times L. Similar thing where I'm going to write the enthalpies just by numbering them. H3, H4, H5, and H6. Now we get to what do we do with calculating the enthalpy. So if I just go back up to my energy balance, remember that is going to be the sum of, because I have multiple streams now, the sum of the moles times delta H. So this is going to be out minus in. So Q is going to be equal to, in terms of the stuff that I drew here, it's going to be slightly long, so I'm going to pause the video. Okay, this is going to be my energy balance. So these 4 terms, the first 4, are my outs, and I'm subtracting my ins. And I wrote it backwards, right? So these are my outs. I don't want you to think that this is the in for the table, right? So I wrote it fine. Just want to make clear that this in is for the table, and this out is for the table. Right, but this is what it's going to end up being. So therefore, once I know what my XA, YA, VL are, so once I solve that, I next have to calculate what all the molar enthalpies are, and that will allow me to solve the problem. So calculating these is going to depend on what your substance is. So we'll start by saying that if you have a table of enthalpies, use it. So a table is going to be the easiest because you can just look up what the enthalpies are for the different process conditions. However, this is only going to be likely for water. So if you have other types of chemicals in your system, you probably need to use another method. So the second thing you can do, remember the reason why you use a table is because you have to assign a reference state. So to calculate molar enthalpy, remember this is not something that you can calculate in an absolute manner. It has to be relative to something else. To calculate molar enthalpies, set a reference state. And this is why you would use the table, because you would just take the reference state of the table. So the most convenient choice of reference state is going to be the inlet conditions. The inlet state, so the inlet T naught and P naught is a convenient choice. And the reason why it is a convenient choice is because say your inlet conditions are T naught and P naught, you choose to set the reference at T naught and P naught, you would automatically know what molar enthalpy of 1 and molar enthalpy of 2 are going to be. See if you can guess what those values are. And remember that if the reference conditions is equal to my conditions of the component, I don't have an enthalpy. So these would cancel out as 0 if I set my reference conditions to be T naught and P naught. So that's why it's a convenient choice, because you can eliminate some of those enthalpies. But now I need to figure out what to do with H3, H4, H5, and H6. So if I set the reference to be the inlet temperature and pressure, then I have to calculate the enthalpy of the conditions relative to those reference conditions. So let's start with just calculating H3, and then, let's start with H5. It's going to be a little bit easier. Calculating what H5 is the specific enthalpy, or molar enthalpy more correctly. Molar enthalpy of component A, liquid component A to be even more specific, at T and P relative to liquid component A at T naught and P naught. And let's assume that we are changing temperature here while keeping pressure constant. So for separation processes, probably are going to have 1 atmosphere. We're going to assume that P naught is 1 atmosphere as well, and we're getting there by changing temperature. That's what we're likely to have most often. So you've got T that is higher than T naught. Remember from your MEB class, how do you figure out what the change in enthalpy is relative to these process conditions for changing pressure? And for that, you can use the Cp value. So it is the integral of Cp dt. So H5 is going to be equal to the integral from T naught to T of Cp of liquid A dt. And you can go multiple places for these Cp values. You can get these from the back of the Felder, Rousseau, and Bullard textbook. You can also get them in the back of the Lane textbook, if I'm not mistaken. These are most oftentimes listed in polynomial form. So it's not too difficult to take an integral of a polynomial, but you want to review how to do that. Similarly, H6 is going to be the same thing. So H6 is the integral from T naught to T, Cp of liquid component B this time instead of component A, dt. So H5 and H6 aren't too big of a deal. You just have to take an integral. So H3 and H4 are going to be slightly more complicated because it's going to be the enthalpy of vapor component A and B relative to liquid. So remember that this presents an issue because we cannot just take the heat capacity of liquid A, but we have to incorporate the fact that vapors and liquids have different heat capacities. Remember from MEB, the way that we conquered this is by constructing a hypothetical process path where we would start by sending liquid component A to its boiling point. So we'd go from T naught to T boiling of component A. So we'd have to look that up in the table somewhere. And that would be the Cp of liquid A dt plus, then we have to perform the vaporization. So in performing the vaporization, the relevant enthalpy that we need is the molar enthalpy of vaporization for component A. And then we have to go from the boiling point of component A, because that's where the boiling happens, that's where the vaporization happens, is at the boiling point. So plus the integral from T boiling of component A to our process temperature T, Cp of vapor A dt. And H4 is similar, but just for component B. So clearly you can see that H3 and H4 are going to be the most complicated calculations in this entire problem. Now I want to note that you can't circumvent this by choosing a different reference state. So once you choose a reference state, you're stuck with it. So you might say, well, instead of choosing the inlet as my reference state, maybe I want to choose the outlet as my reference state. And you could do that, but you still would have the same amount of work. It would just be in a different place. So try to rationalize that yourself as maybe practice, say, setting the outlet temperature and pressure as your reference state and see if you could calculate what the energy balance would be. So after all that, you would then plug it into this expression. Once you have your 3 through H6. Remember H1 and H0 we were canceling because we set the reference state equal to the entrance state. And from there, it's just plug and chug to calculate your energy requirement. And then if you know what the cost of electricity is, you know how much it would cost to run your single stage distillation unit. That's all for this video.